So again, this is our fourth and final form of transformation called dilations. Get one document up for me. All right. So a dilation is a reduction or an enlargement of a figure with respect to a fixed point. So you noticed here on the left, I've got a single point going out to A and B and C, and then I go out along those same lines, double the length, double the length, double the length. In other words, based on this point, I'm adjusting how long to the vertex. That point is called the center of dilation. And it allows a dilation to be an example of non-rigid transformation. What that means is that you're not producing a congruent figure. All the other ones do. In this case, the legacy that it leaves is smaller or larger. It leaves a similar figure. And we'll learn about this later, but similar figures like ABC and A prime, B prime, C prime do have the same angles. But the sides are going to be proportional. In other words, if this side is twice as long as this side, then this side will be twice as long as this side. That idea that it's twice as long is actually called the scale factor. We normally use a scale factor of K, variable, to indicate that it's a scale factor. And whenever we're multiplying by a K that's greater than 1, the dilation is an enlargement. Whereas if K is less than 1, the dilation is a reduction. I guess really it should be absolute value of K is less than 1 because it should be a fraction. And just as we had rules for the translation and the rotation and the reflection, we have a rule for dilation, and it's really easy. If I have an initial point xy and I want to undertake a dilation with a scale factor of K, all I do is multiply each value, K times X and K times Y. And that's my new point. It does only work if we're centered at the origin, but that's the way we're going to do it for now. For example, we're given a triangle RST, and we want to apply a dilation with a scale factor of 2. So let's please plot RS and T. And we are going to be making a fair number of lines today. So if you have a straight edge, you should take it out. If you don't, I have some here I can lend you. Let me just finish this and I'll do that. All right, so I start with this triangle, and then I want to apply a scale factor of 2. And there is a way to do it just from the picture. In other words, I could see how I get to T. Looks like it's over 2 and down 1. And I can apply that same over 2 and down 1 again, and that would be double. But I'm going to suggest a different path for this in general. I'm going to say we're going to use our formula up here. If the R point was -5, 1, that's our starting point. And we're just going to multiply K times each part. So K is 2. What's this going to be? -10, 2. And if T was 2, -1, what's T prime going to be? 4, -2. And if S was -3, 4, S prime is -6, 8. Now we can plot those points. Any questions about applying a dilation with a scale factor greater than 1 so that we end up with an enlargement? Okay, let's flip to the next page. And let's do a reduction, which means we're going to be seeing what? A smaller scale factor, right? Like 1/2. So let's start by plotting the point. -10, 2 is J. -2, 2, 4, 6, 8 is K. 2, 4, 6, 2 is L. -2, 2, 4 is M. I really would rather you didn't. Oh, sorry. I mean, you're here now, but. First time in 7 years that's happened. Historically, and again, we're just going to use our rule here. If J was -10, 2, what's J prime? It's just half as much, right? -5, 1. And let's plot that. 1, 2, 3, 4, 5, up 1. And is that halfway between the origin and J? It is. K is -2, 8. So taking half of each of those would be -1, 4. -1, 1, 2, 3, 4. And again, that's right in line. It's halfway to K. L is 6, 2, so L prime would be 3, 1. And M is -2, -4, giving me -1, -2. You should end up with something that looks about like that. Let's take a look at number 5. Is this an enlargement or a reduction? It's an enlargement because this is bigger than 1. 5/2 is like 2.5. But because it's a fraction, it's going to be a little bit harder to work with. So if e is 2 comma 4, what's e prime? 5 over 2 times 2, and then 5 over 2 times 4. Right? Our k is being multiplied by each one. And this messes with people. How do we do this? Good. It's a fraction times a whole number, which you can't really do by itself. So we turn the whole number into a fraction, 2 over 1. And now you can treat it as 5 times 2 all over 2 times 1. Do the same here. We get 5 times 4 all over 2 times 1. And you have a choice. You could just multiply them out and you get 10 over 2 comma 20 over 2, and then reduce that to say that's 5 comma 10. Or you could recognize that this 2 and this 2 cancel. So that leaves just 5 on the left. And this 2 and this 4 cancel, leaving an extra 2 up there. So 5 times 2 over 1 is 10. Either way gets you the same answer. Would you please do point F for me, just to make sure we're all getting the same answers? Show me what F prime would be after a scale factor of 5/2. Count of 3, would you please give me the x value of F prime? 1, 2, 3. Excellent. Count of 3, give me the y value. 1, 2, 3. Very good. Any questions on finding the resulting points from a dilation with a fractional scale factor? Yeah.
So for number 4, it's 1/4 that's less than 1.
Right.
So you would just do like you would do, or like how would you set that up?
You would just multiply everything by 1/4. So what's 1/4 of -4? -1. What's 1/4 of 8? 2. What's 1/4 of 10? 2.5. 1/4 of 0 is 0. And so you'd be able to then plot these points. When you plot 2.5, it's going to be 1, 2, and right in the middle there. As close as you can get. Does that make sense?
Yeah.
Any other questions? Please flip to page 3 and take a look at number 11. What makes that one different? It's backwards, isn't it? They give you the result and they give you the scale factor, and you're supposed to find out the coordinates of the original, the pre-image. There's all kinds of ways you can do this. I suggest we recognize that what we're doing is we're going from xy to kx comma ky. In other words, we're trying to solve these. And we know that kx, in this case, scale factor is 2. So 2x comma 2y is equal to what they gave us here. -10, -8. In other words, the x value is twice whatever the original x is, and it's -10. So that means 2x equals -10. Divide by 2, and get x equals -5. Same idea for the y. 2y equals -8. Divide by 2, y equals -4. So the point A is -5, -4, -4. Could you have just intuited that? Yeah, very possibly. But by having a system or a process, you can do it even if the scale factor is 1/3 or 3/2 or something a little bit harder to work with. Any questions on that? Okay, last piece. Now we're going to go from the pictures. We've got an image and a pre-image. Which one's the image? The ones without the prime? The pre-image is without the prime. The image is with the prime. So this is going from the bigger one to the smaller one. So what do we expect the k will be? A fraction, a smaller number than 1. Now, we need to know the rule here. Scale factor k is equal to image over pre-image. And remember that there's lots of corresponding parts. So for example, if I were to take d prime f prime, which is an image length, and divide it by the length of df, that would give me the scale factor. If I did d prime e prime over de, even though these dimensions are different than those, when you divide them, you'll get this same scale factor. Turns out you can even do it with the coordinates. So let's take a coordinate like d prime. That's the image. So if d prime is the point 0, 2, and d is the point 0, 2, 3, 4, 5, 6, 0, 6, I can pick any part of this point to make my scale factor. Should I pick the zeros or should I pick the 2 and the 6? Yeah, so I'm going to say k is equal to image, the resulting one afterwards, 2 over 6, which reduces to 1/3. Is that less than 1? So does it make sense? It does. And I should find that if I look over for the f, over 2 down 1, over 2 down 1, over 2 down 1, it's 3 times the distance to go to f as it is to go to f prime. Any questions finding the scale factor from an image and pre-image? Excellent. Last piece for today is to talk about similarity. Excuse me, not similarity, symmetry. And I would guess that most of you have actually already spent some time in grade school looking at this stuff. And you know about line symmetry. Like what insects are symmetrical? A butterfly comes up a lot, right? The wings are kind of the same. They're very crazy looking, but each one's the same. Turns out an ant would be too, right? If you drew a line right down the center of its back. Would you say that this ladybug is symmetrical? Why not? The dots aren't right. If I draw a line straight down the middle, the dots are not the same on both sides. Is this shape symmetrical? Sure. If I draw a line straight down the middle, I could fold the paper on this and it would fold right back on top of itself. Correct. There's no horizontal line. That's actually called a reflection in a line. We're looking for it like a mirror, like a line of reflections, all right? And we wouldn't have any others. It would just be this line. Does this shape have symmetry? Well, it turns out it has a particular type of symmetry. Upside down, exactly. It has point symmetry, which means if you hold this and then flip it around 180, it looks the same. So this shape has something called point symmetry. And then this last one is called rotational symmetry, which is a lot like point symmetry, but instead of having to go all the way around, it can go in smaller increments. Do you agree that this little triangle could go to this one right here, or there, or there, or there, or there? There's actually 8 different spots where that first triangle could go. And any one of those would be exactly the same looking shape, gentlemen. Therefore, I can take 360 and divide it by 8. And that tells me that this has rotational symmetry of 45 degrees. If I rotate this exactly 45 degrees, it'll look the same. And if I rotate it another 45 degrees, it'll still look the same. So what about this regular hexagon we've got here? Does it have line symmetry? Sure. There's one. There's one. There's one. It's got a bunch of them. Does it have point symmetry? If you flip it upside down, would it look the same? Sure. Does it have rotational symmetry beyond 180 degrees?
Yeah.
How many different places could this side go and look the same? 6. So if I say 360 divided by 6, I can say that this has 60-degree rotational symmetry. Okay. That's all I've got for you. You have the rest of the period to work this out. Post it in Canvas, please. The period is yours.